Hey everybody, it's Craig Maynard, Senior Mentor for FRC, First Robotics West in Western Canada again. And we're back to another one of our First Labs live streams. And today is a good one. Our theme today is Java Jumble. And we're going to start to introduce you to some of the concepts of Java from very basic to very advanced levels, and maybe set you up with some resources. And our guest today is Richard McMullen from Toronto. He's a lead mentor for Team 1310 Runnymede Robotics up there, and he's also has incredible resources and applications to help us with get our mind wrapped around Java. And hopefully you've got some Java experience out there. So we're going to assume that you've done a little Java programming, and Richard can pick us up from there. So are you there, Richard?
Yeah, I certainly am. Thank you for the introduction.
Oh,
So, my name is Richard McMullen, and I am the programming mentor for Team 1310.
programming
Our
mentor.
head mentor, yeah, our head mentor is Richard Yusui.
Okay.
He's a teacher at the school. Runnymede is a high school in Toronto. We're in the West End. And what we've tried to do this year is bring a bunch of teams together and run some programming lessons to try and elevate the level of coding. Everyone has been crying out for Java coding lessons, and we thought we would do it this year. So we're running 4 weeks, 6 hours each of Java lessons, so 24 hours. And right now, tonight you're going to get one of the hours, our intro hour of the 24. There's a little bit of feedback, so I don't know whose mic that is, but if you want to mute your mic,
All
then
right.
we can. There won't be as much noise. So today, here's the Runnymede website, which hopefully is on your screen. And what I wanted to do was take us over to the Toronto Coding Collective. This group of teams, East York Cybernetics, NACI, MaxTech, Wolverines, R3P2, Paragon, CyberHeart, JPCI Jaguars, and Hargarth Hornets, along with Runnymede Robotics, are forming the Toronto Coding Collective this year.
Very
Every year
cool.
it's a different makeup. And every year we kind of start from scratch with the framework so that people have a chance to learn what it is, how to program a robot properly, how to structure the layers of code. And so we have these lessons that people can sign up for. As you can see, there's a sign up sheet. Don't sign up if you're out west. We don't broadcast them over the internet. But if you can make it to Jane and Dundas in Toronto, you're welcome to sign up.
All right.
So let's go over to the Toronto Coding Collective website, because this is where we keep a lot of the work that we're doing. It's on an ongoing basis, and we talk about how to install the code, how to run the code, and there's a lot of really useful links here. So in getting started with the Toronto framework, you need to install the Java tools and the FRC tools. And so this little thing here, who we were last year, who we are this year, so you can see it's growing, and it's a brand new thing, so it's not that old. So under install notes here, we have two sets of install notes. We want to install the Java development tools and the FRC tools, and then we want to install the Toronto framework that the Toronto Coding Collective has put together. So let's look at installing the development tools. Java coders in installing the development tools need three main things. You need the Java JDK, and that is downloaded from the Oracle site. And there's a link right here that takes you exactly to the download site. So here we go. And here it is, the Java SE Development Kit 8U151. It runs on Windows and it runs on Mac and various Linux. You can develop robot code on Mac. However, in order to run the robot code, you need to run something called the driver station, and really it's only running on Windows. So although you can develop on Mac, you need a Windows machine in order to run the software. So the one that you want to download is probably this one, Java 8.151. And people have asked me, what about 152? Should I download 152? It really doesn't matter. 151, 152, whatever. either one of these will work. And people have asked me, so either of those will work. So once you've downloaded and installed Java on your PC, you then want to download the Eclipse IDE. And there's a few tips and tricks here, so I'm actually going to take you through it. I've downloaded a version of Eclipse that I have, and I've unpacked it in a folder under my software directory for the FRC demo. So here's my Eclipse. All I've done is download the package. I put it in my downloads folder, and then I unzipped it here under software FRC demo. You can unzip it under C users, whatever your name is, and then unzip it there. It really doesn't matter where you unzip the Eclipse package. It just runs from here. So once you go into the first Eclipse package, the first thing you're going to see here is the Eclipse EXE. Okay, so this is, you don't want to go find this every time. So what I do is I create a shortcut as the first thing, and then I copy that shortcut to my desktop, and then I'm going to rename it first, FRC demo. And then we're going to open this, and I don't always want it to ask me, so I'm just going to run it. And this is Eclipse Oxygen, so this is the latest version of Eclipse. I didn't show you that download site, but it's pretty straightforward. You can find the Eclipse version that you want and download it. So now it's gonna start up here. So I'm gonna go back here. Yep. Okay. So then when it downloads, the first thing it asks you for is a workspace, and it probably wants to put it under C users, Richard, but I'm using that already. So what I'm going to do is I'm going to put it under my software directory that I just had open.
Okay.
FRC demo. There's my FRC demo, and I've got Eclipse, and so under here I'm going to actually create a workspace. New folder, workspace. Oh, clicked on the wrong spot there. Workspace. Okay. See FRC demo, the workspace.
Yeah.
And I want to use this as a default, and don't ask again. And we launch. So now it's going to open Eclipse.
Here it comes.
Here it comes. And it's what it's going to do first is what it's doing the first time is it's installing some packages on your machine, and then it comes to this lovely screen here, which is the welcome screen.
Welcome.
And typically you don't want to see the welcome screen. What you want to see is the developer workbench. So I click this off, and then we go to the developer workbench, and this is a typical workspace. It has a package explorer, which is you're going to see is going to show all my projects. On this side, it's got a task list, which I don't use, so I'm just going to close that. And then this is really important, the outline. So whenever I have a Java program running here, the outline is going to show up in the other box. This is where the console runs, and there's a bunch of stuff, and I like to have more space to develop code, so I move this over under here. And now I've got a nice big space to develop code in the middle here. So now, configuring Eclipse, really important. So there's 3 key steps. Unzipping the Eclipse JRE and running it, Eclipse package and running it, which we just did. And then ensure the Java JDK is not the JRE. So under Windows Preferences, Java, there's installed JREs here. And right now it says JRE 8.1.144, but that's not what we want to use. We want to use the Java Development Kit that we just downloaded and installed before.
Right. So
that's going to install under C:\software, this PC, program files, Java. There we go. And I have a lot of JDKs. I should have cleaned this up, but I'm going to use the latest one. And then it automatically fills in, and you click Finish. And now you've got a JDK that you can configure. You select that JDK, and now you're ready to go there.
So JDK is Java Development Kit?
Java Development Kit, thank you. Yes. Versus Java Runtime Environment. So Java Runtime Environment is what's going to run things on the desktop, and the
Right.
Java development kit is what we need in the FRC, in the FRC Eclipse.
Does that have all the
So that,
libraries? Yeah. Yeah.
yeah. So then we want to install the plugins for FRC. And actually, I think I've done this before, and I want to make sure that I don't have that already there. Is it WPI lib? No, I deleted it. It's all set. Okay. So what we want to do is we want to copy this URL, and we're going to use that as an install site on our Eclipse. So under Help, Install New Software, we're going to paste in that address. And then when you hit Enter, it's going to show the WPI lib robot library. And you just click that.
Crazy.
Next. And it's going to install both the C++ and the Java development environment.
Right from the WPI website. Wow.
And you accept the terms of the license agreement, and you're done. And then it installs the software. This doesn't take very long, maybe about 15 or 20 seconds.
Incredible.
And then what it's going to do is it's going to ask me to restart this Eclipse because it's going to put new features in. In here, there's project run and window, and what you're going to see is WPI lib is going to show up somewhere in here in the top of your Eclipse environment after you do this installation. So this is part one of the installation. Right. And then what happens is when you create your first project, it actually starts installing some more stuff as well. So I'm gonna show you both of those things because they're a little bit fancy or
convoluted.
Yeah, a little bit. But it's not that hard to follow these instructions. So, right here you have it in 3 easy steps, 1, 2, 3. It takes me back to my welcome screen, which I said, don't show this at startup. And see how it's starting to do all these extracts?
Right.
This is where it's installing all the WPI lib under my user profile under C users. Wow. In my case, it's Richard, but it would be whatever your name is. And then it's going to start installing those. So then once that's done, we can go to the workbench, and you'll notice up here between project and run, there's now this new thing, WPI lib.
It's new,
right?
Yeah.
It's new because we just installed the WPI lib. You don't need that. I never go there. But what you do need is surprisingly under here you can't set your team number, but under preferences you can. Window preferences, there's a new WPI lib preferences here.
Oh, look at that.
And so I'm going to set it to 1310 because that's my team number and that's my robot number that I'm going to download to, right?
Good idea.
Apply and close. So there you go. So now I've done step 4 here, set the team number in Eclipse, and then step 5 is create your first project to complete the setup of Eclipse variables for FRC, the network tables, and WPI lib. A little bit fancy, I'll just show you that. Under Window Preferences, if we type in variables here, Java class path variables, it has a bunch of variables here. So it's got the JRE, it's got a home, JUnit home, and M2 repo. Okay, so we'll leave that the way it is. But now I'm going to create my first robot project. New, other. See, now we have WPI lib stuff here. WPI robot library. And we're going to create a robot Java project next. And I'm just going to call this temp or something like that because I'm not actually going to use this one. And I don't like the package names being quite so long, so I delete that and I just make it robot. And we're going to use a command-based robot, and I'm going to have that there just for this demo so we can compare the Toronto Coding Collective with this temp later on. So I click Finish. And now see how it had a little red X there for a second, and then it's done a whole bunch of stuff. And now under here, we can see it's created some source files for us. It's created a robot commands, and robot subsystems, and under there, it's got a bunch of different stuff. Okay. And when we go to Window Preferences again, now look at this class path variables all filled up with things like network tables, OpenCV, and WPILib resources are all in there. So when you create your first Java project, it actually finishes the configuration of Eclipse. And now this is ready to go, so I can actually run this project. So run as WPILib Java deploy, and it's going to start compiling this code over here. And I know that you saw that, so I'm going to make it a little bit bigger. So what it does is it tries to build everything, and it worked. And then what it's trying to do is connect to the robot to download this code. So the build worked, and now it's trying to download the code to the robot. But there is no robot because I'm connected to you instead of to the robot, so it can't find the robot. So that's what this is. That's what this is saying. If there was a build error, it wouldn't compile correctly, and you wouldn't get to this step. So once it's trying the target, then you know you're at that step. Okay. So really, that's it in a nutshell. You're set up to start developing your robot code.
Wow.
Just like that.
That's fantastic.
Yeah. That's all there is to it. So, and it would have compiled and it would have downloaded to the robot, assuming that the robot was configured correctly and the robot was there and ready to receive that file. So now I need to show you a little bit more. We'll go back to the install notes, and we'll talk about the FRC software components for a minute.
Okay.
So in the FRC software components, what do you need to develop and deliver to make a robot? Well, there's a lot of documentation on WPILib and the software component documentation. If you go here, you can see it all, and there's lots of stuff to look at. And every one of these has links, and you can go everywhere and sort through it. So that link is there, which is really nice for those that want to explore. And for those who want to just get right at it, what really do I need to know? We talked about installing the development tools, but then there's also the driver station, which you need to install, and the smart dashboard. And then, so if we click on driver station, it's going to show you exactly the driver station here, and here's where you find the development suite, and then you just start installing. Okay?
Wow.
And there's lots of notes here, and you can just follow these and install the driver station. And again, this is for Windows. It doesn't work on Mac. There is no driver station for Mac. So this is what helps you.
Yeah, I love Screen Steps.
I do too.
Yeah.
You know, what would we do without it?
I know.
This is where I got all my knowledge. I didn't get my knowledge from anywhere other than here. So
incredible.
Really, it's our job to point you at the right resources, right?
That's the one right there.
So there you are. So that's driver station, and then smart dashboard is something that we use to display robot values when we're connected to the robot. However, the next step is really, really important, configuring the robot. You need to configure your robot. So there's a RoboRio imaging tool, and it's not the world's most friendly piece of software, I gotta say. It's not hard to use, but the RoboRio imaging tool, it says here, click on that. Well, that's under C, Program Files x86, National Instruments, LabVIEW 2016 Project RoboRio tool, and then you click on the imaging tool. And once you've opened the imaging tool, you now might want to image the RoboRio. So you have to go find the file that you need to image the RoboRio. And once the imaging, or click on it'll be there. You don't need to find it, it'll be there. And then you click on it, and then it's going to update the RoboRio. Now you have to be connected to your RoboRio with a USB cable, and it describes all that here and where to plug it in and all that. So this is a really, Screen Steps Live is a really great spot, and you can spend the time, and if the steps are clear, you just got to take the time and go slow and just go through it.
Beautiful.
It is beautiful. It's really beautiful. So FRC has done a fantastic job there. And then the next step is installing Java 8. So once you configure the RoboRio or image the RoboRio, it's now wiped. So everything, all the Java libraries are wiped. And you need to install Java 8 on the RoboRio before you can install your program. And there's some steps. Again, Screen Steps Live tells you how to install Java 8 on the RoboRio. And you just go through it. Step by step, nice and
Incredible.
easy, right? So there's so much. The only reason that I put this together as a website is because there's there's so much under the FRC software component overview that you can get lost. And so if you're a Java programmer, what are the minimum things that I need to do? I need to image the Rio, install Java 8, and configure my radio.
Mm-hmm.
Once those three things are done, I can connect my laptop to my radio, download my code, and my robot just starts driving.
Hmm.
So it's as simple as that.
Just like that.
So we're just like that, just like that. A couple of useful things around the RoboRio dashboard. So there's a RoboRio dashboard, and I'd love to show you that, but I can't, as we said, because then I wouldn't be on the phone. But when we connect to the RoboRio, there's a dashboard, and you get to it by typing this address in your Internet Explorer web browser. So it's not Edge, not Firefox, not Google Chrome. This is the old IE 11 or whatever it's at now. You got to find that on your computer and actually pull up IE and type that in, because it uses Silverlight.
Oh.
So you need a browser that supports Silverlight.
Yeah.
Or have Silverlight installed on something in order to connect to the RoboRio dashboard.
Yeah.
The RoboRio dashboard we use to upgrade the firmware on Talon SRXs, to upgrade the firmware on our pneumatics control port module, pneumatics control module, and on our power distribution board. So when you go to a competition, they ask you, can we see all your firmware versions and make sure that they're all correct? And it's through this tool that you do those updates to the CAN bus devices that are connected to the RoboRio. Right?
Yep. I remember that.
Makes sense?
Yeah, I remember that.
You remember that?
Oh, yeah.
So this is everything you need now. Like, you shouldn't need much more than this unless, you got Vision stuff installed. But if you're running a basic robot, you're ready to go. You should be ready to go at this point.
Incredible.
So what do you think of that?
I love it.
It's pretty good.
What's the usual, is there any major hiccups these kids usually have when they're installing for the first time? Any roadblocks? That's quite common. Or if you follow these steps, is it pretty transparent?
It should be. It should be. I've had some issues with connecting via the MDNS stuff, but really with Windows 10, a lot of that's gone away. Like it was harder with Windows 7.
Really? Oh.
But with the Windows 10, I think it's all just kind of, it's gone away, and the installers work, and things are just working a lot better these days, I gotta say. The FRC software, if you follow these steps, I mean, I followed them earlier this year and was able to get a robot up and running in a couple hours.
Yeah, yeah.
And so it wasn't that hard.
Mm.
So do you want to talk about Java code and how to actually program this robot now that we've got it all ready?
I think that's a logical place to go.
I think so too.
All right.
So you'll notice when we went to Eclipse here, I'm going to pull up Eclipse, and I'm going to pull up the code here. We have a few classes that come built in, and those are the operator input classes, or the OI class, the robot itself. There's a robot map, and they have an example command and an example subsystem. They have this robot triggers that nobody ever uses and nobody ever needs, so you can just delete that, because there's no point in having a package that you're not going to put any code in. Okay. I've never used it, never in my 4 years, and we run fantastic autos all the time, and we've never used the trigger package. So
sounds like a challenge.
There's only 5 classes. Yeah, sure. Maybe you can find a way, find something useful to do with it. So there's only 5 classes here, so it's really not that much code to go through. And I think what you want to do is understand the structure of these layers. Mm-hmm. So I'm going to go back to the Toronto Coding Collective site here for a second and talk about the command-based robot. So again, all this is up here. You can just go and read through it at your leisure, no problem. And this material is going to grow over time. So the first thing, the objective of the command-based robot, we want to look at why did they build it? Like, why did they make this WPI-lib command-based robot? And if you read from the WPI-lib website, it says it supports a method of writing programs called command-based programming. And command-based programming is a design pattern to help you optimize your robot programs. So I agree with that. And specifically, it talks about activities happening over time, activities happening concurrently, and it's desirable to test the robot mechanisms and activities each individually before you try and orchestrate them into a full autonomous. It'd be nice to test, can I make the robot consistently go forward 30 centimeters or 30 inches or 90 centimeters consistently before I start integrating that into my overall auto pattern. You know what I mean?
Yeah.
Like if you can debug these individually, that's a good thing. And often programs need to be augmented with additional autonomous programs at the last minute. And this was somewhere where Runnymede has really had success over the years. What we've been able to do is in the queue write an auto based on the actions of our fellow team members in order to avoid them or in order to do something special or novel, and they've worked.
Yeah.
So you've been able to write them in the queue and execute something out on the field.
Just like that.
Just like that. So it kind of makes sense though, because if you can, have you ever programmed an FLL First Lego League Lego robot?
Oh, lots of time.
Have you ever done that?
I'm the FLL tournament director down here. It's one of my hats. Yeah.
So an FLL robot, they have nice commands. You can say go forward this many rotations, turn this much, then go forward that other number of rotations. Yeah. Well, you have to build that all yourself in the FRC code. It's not plug and play like that. So the objective of the robot framework that we're building is to try and create that plug and play, that plug and playness. You know, the way to be able to write these complex auto patterns and orchestrate movements of arms and wheels at the same time, and in a way that's easy to maintain and that's robust under tournament conditions. So the structure of the layers of the code are there's three main layers. If we look at the bottom, there's the bottom layer is the subsystem. So that's the hardware. And you can define multiple subsystems on a robot. So you might have a drive-based subsystem or chassis subsystem, an intake subsystem, a shooter subsystem. Last year you might have a gear hanger subsystem, a vision tracking subsystem, a climber subsystem. And each one of those has a series of motors and sensors associated with it. And really that defines a subsystem. And what you want to do is create methods that external commands can call to update that subsystem in a periodic way. So, for example, on the chassis subsystem, you're going to have a left motor and a right motor, or multiple left motors and right motors, depending on how your speed controllers are configured, either in follower mode with Talon SRX or just regular Jaguar controllers, and plugged directly into PDP ports on the RoboRio. So you've got a left motor speed and a right motor speed that essentially that's what you're trying to set, right? So you need to have a left motor speed and a right motor you need a set speed command.
Right.
And on the sensor side, from the chassis subsystem, you definitely want encoder values coming back off of those motors.
Yeah.
Because you're never going to be able to control them without that encoder feedback.
You're
not going to be able to walk a certain distance. Maybe you are if you have external sensors like ultrasonic.
Maybe. But dead reckoning never works.
Dead reckoning never works, right? Because the things can slip, and then the third piece that we have on our subsystem is a gyro. So for us, a chassis subsystem is a gyro, left-right motor, and left-right encoder. That is a chassis subsystem, fully described. And if you have that, then you can build that up in many ways to make more and more complex patterns out of that, because your gyro is a compass and it's going to tell you where you're pointed. I'm pointed to 0 degrees. I'm pointed north, and then 90 degrees is I'm pointed east, and you can navigate your way around the field using that gyro, the encoder feedback for distance, and just using the speed controllers and some PIDs, proportional integral differential controllers. So up at the top level, we have joysticks, though. So there's a couple of, I like to think of it as an operator input layer. And this is something that's not very well done in the framework that's handed to you. There's just one class called the OI. I think of the joysticks as there could be a game controller. I might use a PS4. I might use a Xbox One controller, or an old Xbox controller, a Logitech controller, different joysticks, and really having those work in sort of a transparent way is difficult, because I don't know if you know this, but on all the game controllers, the button maps are different.
I noticed.
So you've noticed before, yeah. So we try and we're trying to build a little interface around the joysticks, and I'll show you that in a couple minutes. And then tying the joystick interface and the auto selector to the subsystem is something called a command. And the command takes input from the operator in some way and drives a subsystem. Now, we mentioned that there are multiple subsystems, but there's only one controller, right? So how do you make that work? You have a separate command that's running over each subsystem that's reading the joystick independently, and that's how you can get independent operation. So you might have more commands running, more than one command running at a time, right? And this next section on commands tries to explain that a little bit, but what it also does is we want to look at, if we look at the diagram, is just kind of a diagram of the basic elements of a command. A command is constructed at some point on the Rio and sent to a scheduler that's running in the background. At some point, the scheduler is going to pick up that command and start running it. And when it first runs it for the very first time, it calls an init method to just once to let your command know you're about to start. And then what it does is it calls this execute loop every 50 hertz, every 20 milliseconds. It calls your execute loop over and over again. And it also calls the isFinish routine. And when your command is finished and you return true from the isFinished, then it calls the end routine. So basically it falls through that flow. Now, there's a few gotchas here. If you're going to eventually orchestrate your commands into a command group that you're going to use in an autonomous program, in your Java constructor, you don't want to do things like read a sensor value, because you have no idea when that command is going to get run. So in your constructor, you want to pass in parameters that you're going to save on your command, and it might go into a big command group, and the command won't get run till later. So a good example of that is, let's say I have a command that I want that turns the robot 90 degrees to the right. I turn right by 90 degrees. So I'm going to go forward, and then in my auto command, I'm going to go forward, I'm going to turn right, I'm going to go forward again, and then I'm going to turn right again. So imagine I was trying to do something on the back of the tower this year or something like that. So the first time if I get my current, and the way that I turn right is I look at my current heading and then I turn right 90 degrees, right? If I do that in the constructor, I know this is really complicated, but if I do that in the constructor, all the constructors all happen for an auto command before the robot even starts moving. So it's pointed 90 degrees north. So the current heading is 0 degrees all the time. So when it does the first turn, it's going to go to 90. Then it drives along. Then when it's going to do the second turn, well, the finishing point for the second turn is still 90 degrees because its initial point was 0, and it doesn't know that it's now at 90. So if you want to know that it's now at 90 when you're doing the second turn as your starting point and you want to go to 180, then you need to do that in the init method, not in the constructor. So be careful about reading any values from any sensors in the constructor and saving them for later. They're not right.
Yeah.
They'll only be correct if you get them in the init portion of the command. So that's a little gotcha that we've run into a few times, and we'll probably run into again because we do that and make the same mistakes, but we'll find it again, so no problem. Then in the framework, if you read through the Java WPI documentation, it says it calls execute then is finished, which is normally the way you would think about it, but that's not true. It calls is finished before it calls execute. So you can finish a command before it even starts. So if you're looking for an arm to be at a certain number of degrees, it won't start moving the arm before it checks. It's going to check the final state first, if you know what I mean. Does that make sense?
It makes sense.
So it's always going to call is finished before it calls execute. So think of is finished as the middle layer. Like every 20 milliseconds, the first thing it does is call is finished. And if it's not finished, then it calls the execute portion. And then if it is finished, then it swings off to the side and calls the end. So that allows you to do anything like turn off motors or do any cleanup that might be happening to global variables.
And it polls at every 20 milliseconds.
Every 20 milliseconds.
Yeah.
So the key element here that you need to think of as a Java coder is FRC code should be really simple. You only use if statements or switch statements. You never write a loop.
Oh,
so you know how in the Canadian computing competition, it's all about loops and figuring out how to loop around stuff. You never write a loop in your robot code because the loop is happening by the FRC framework itself. So you're reading a sensor and then running some if statements over it. You shouldn't be, for sure you shouldn't be executing a loop.
No.
Because all of your code has to execute in 20 milliseconds. And that's pretty easy. I think a lot of robots spend about 70% of the time doing nothing. So really, you should be able to execute in, 6 milliseconds.
Yeah. I guess there's a hazard of getting into an infinite loop, too, if you're not careful.
Yeah, and if you're doing something complex, you can easily, if you're not careful, you can certainly get an infinite loop, but you could also burn through the 20 milliseconds and throw everything off.
Yeah.
Right? Then you end up with communication failures starting to happen. So if your robot is unreliable from a comms perspective, it could be that you're using up more time than is available. You're using all the CPU.
Yeah.
Right. So from here, maybe what we should do is, now that you see this, is look at the code that first gives us around the around those areas. So let's pull up our example command, and you're going to see exactly what we talked about before. So here's an example command, which extends command, and one of the interesting things here is it requires us the example subsystem in order to run. And what this does is it locks two commands from executing at the same time. So any command that requires a subsystem will interrupt the previous command that was running on that subsystem and take it over, basically. And so you got to be careful about launching commands, especially off of buttons. I don't actually launch any commands off of buttons. I launch them from the main default command for subsystem. So we have the example command is here, and it tells you which subsystem it's going to use. This is the initialize method that's going to run only once when the command is scheduled to run. The execute command the execute loop is going to be where you put here's where you put all your code, is in the execute loop. And then the is finished is going to return true when you're done. In this case, this is a default command for a subsystem, so it's never going to finish. It's just going to get interrupted by something else. And then after it finishes, it could call end. In this case, there's nothing to end because we never finish this command. And interrupted allows you to do something if you're interrupted from some other command interrupts this command. I never use this. I never use the interrupted. Maybe I should be. I don't know. It's something that in the 4 years of coding that we've done, we've never ever used interrupted. Have you ever used interrupted?
No, can't say I have.
No.
You're talking about
no. So I usually have.
Yeah. You're talking.
I usually have the students delete that if they're not using it because it's confusing to them, right? They don't. What am I going to do? What should I do here? Right. And typically, if you're interrupted, the other command that wants this subsystem is going to do something anyway, so there's no point in stopping the motors. If the other command wants the motor stopped, it'll stop them, right? So that's kind of the way that I approach it is there's nothing really that you're going to do here when you're interrupted. Now, for completeness, they have it, but I never use it. So let's look at an example subsystem now. So the example subsystem, the only thing this subsystem has is a init default command. Not so useful. Well, useful in that you want to init the default command, but the code is actually commented out. So it really should be, in this one, it would be the example command, new example command. Right? Spell that right? Yeah, there we go. New example command. And then that would be the default command that's for this subsystem. So now whenever no other command is running, it's going to run the example command. So far the framework doesn't do very much. It just calls a bunch of commands and there are no motors, so it doesn't do anything. In the robot, let's look at the robot and see how that's structured. So even though we chose command-based robot, the command-based robot extends iterative robot, and it just adds the command functionality to it as well. So at the beginning, you declare all of your subsystems, and they're declared as static final for an unexplained reason that I can't figure out. I think they want to be declared static final because the code looks to see if you're using any ports multiple times. So if you plug a motor 1 into PWM1 and then say ARM1 is on PWM1, the code blows up. It doesn't work. That code won't run. And it'll give you a really cryptic error message in the driver station console, something like robots never die, robot init could not complete properly or something like that. And it doesn't tell you that port 1 is overridden more than once. And you have to go looking for it.
But it compiles okay.
But it compiles.
Yeah.
It compiles fine, and then it downloads, and then it gives you a real nasty message in the console. So one of the ways that we get around that, or try to get around that, is we always specify things in the robot map, and we'll look at that in a second. So in the robot init, here's where it declares the new OI, and it also adds a chooser, an autonomous chooser on the OI in the smart dashboard. Okay? I wouldn't have any of this code here. I would have done OI equals new OI and then OI dot init maybe, and then had your OI deal with the chooser, because it doesn't belong here in the main robot, right? No. I think, like, just from an organizational point of view. Disabled init is going to run the first time your robot is disabled, and then after that it's going to run disabled periodic every 20 milliseconds. In autonomous, it's going to run the autonomous init once. So in this case, it's going to get the selected autonomous and start the command. You don't actually have to do that. You could schedule the command, but you know, this is a different. And I also don't like this because of the bracketing. I would have done this just to make it nice. Like, I recognize that the other syntax is valid, but for beginner Java programmers, just always put the brackets in. It makes your code much easier to read.
Yeah.
And then autonomous periodic runs, and you'll see all these periodics are the same. Scheduler getInstance.run, teleup, scheduler.getInstance.run, and up here, disabled scheduler.getInstance.run. And what that does is it just goes to, there's a scheduler in the robot, it gets all the commands that are currently running and runs them all, one after another. So it gets the instance of the scheduler, that's the main scheduler that's running, and then just starts running any commands that need to be run. So there could be multiple commands that get run here, right? You could have a default, remember we talked about having multiple subsystems.
Yeah.
You could have multiple default commands on every subsystem, and it could be running multiple commands simultaneously. One could be looking for the buttons associated with the arm. One could be looking for the joysticks associated with the chassis subsystem. One could be looking for your climber. So that way you can be driving and still run the climber at the same time, right? There are different commands that are running off of the various joysticks or game controllers that you're using, right?
Perfect.
And then, so that's that. And then this test periodic is for live window, and I'm going to leave that as an exercise to the reader for you to go and look that up and see what that is. So now what I'd like to do is show you how to look at what we're doing. Like, what have we done so far in our first week? We took this framework, and the Toronto Coding Collective has started to extend it to actually move a robot. We had a robot moving. And we put all of our code up on GitHub. So if we go back here, it's the command-based robot, and we go to the install notes, installing the Toronto framework. It talks about setting up your first robot program, which you want to do first so that it creates all those variables. So when you install the Toronto jar, it's not a problem. And then the other thing that it says is eventually what we're going to do is we're going to start supporting the CAN-based controllers. Probably in week 2 or 3, we're going to start pulling up some TAL and SRXs. So when you run our framework, you're going to need to have installed the Across the Road Electronics CTRE web tool, and there's pointers here, and you can just click on those, and it takes you to the CTRE site, and you just download that zip file and install it. And then you'll be set up to be able to use the Talon SRX CAN-based controllers. Okay? And installing the Toronto jar project and the Toronto framework is like I said, it's on GitHub, so you need to create an account on GitHub, and then what you need to do is, here's the GitHub address for it, and here's the Toronto Coding Collective on GitHub. And we've got the Toronto's 2017 jar and 2017 robot framework, and these are built already. These were what we used last year, and like I said, we started from scratch again this year, so if you want to follow along from scratch, you can follow along in the 2018 code. You're going to see it advance a lot over the next 4 weeks. If you want to really kind of where we ended up last year, you can install these. You can download and install these. There's a lot more to them. And we're trying to look at some of the things we did last year and see if we can continue to simplify. Simple is really hard.
Simple is hard.
Writing simple code is really hard. Writing lots of code is not so hard. Writing it simple, clear, well-documented code is very, very hard.
Spaghetti is easy.
So we're trying to simplify. We're trying to simplify. So if you want to see what's going on in the Toronto framework, I'm going to show you how to do that right now. So we go to the Toronto framework, and there's 2 projects, the Toronto jar and the Toronto robot. The Toronto jar is where we're going to collect some classes, and the Toronto robot is going to be that framework that I just showed you 2 minutes ago. That's based on the FRC framework. So in order to clone this, you want to copy this to your clipboard. And then when you go to Eclipse here, you can say File, Import, Project from Git, Next, Clone URI, and it's going to remember and fill in where we just copied that address from.
Wow.
Fills it in already.
Fantastic.
This won't be filled in for you. This is something that I filled in before, and I have for work. Eclipse stores this in one spot on the PC, and it's reused through all the Eclipse environments that you have. So you're going to have to type in your own authentication. And then I would click this checkbox to store and secure store. You're going to need to do that to be able to do pulls all the time. So then you click next, and it's going to say which branch do you want, and you're going to say master. Eventually there's going to be a lot of branches here, but just click the master one if you want to follow, if you're just following along. And then it's going to ask you where do you want to put it. So I'm going to put it back where I had everything before, which was in my software directory in this FRC demo. I'm going to make another folder here that's new folder, and I'm going to put Git. And I'm going to select that folder. Oh, and then I want to actually, hang on. What I am going to do is I'm going to put another folder below my Git directory. That's the Toronto framework. I'm going to put it in there just in case I have multiple Git repositories that I'm downloading from into here. I want to keep them all separate. So you don't want to keep adding. If you go at the base Git level, then every time you add a project, it will go into the Toronto framework, and you don't want that.
No.
So I'm going to make a separate folder for Toronto framework. And then let's say I was downloading some CCC puzzles, or I like to do the Advent of Code every year.
Right.
Shout out to the Advent of Code guys. They do a great job. It's a set of puzzles that's an Advent calendar, starts on December 1st and goes to December 25th. And you do these puzzles that are Canadian Computing Competition. Like really, really, really cool site. Really great site.
How festive.
Very festive. You know, everyone loves doing that. Okay, so save, and then it's going to show me it's going to be Git, Toronto Framework, and then for some reason it copies again. 2018 Toronto Framework is where I'm downloading from. Next, and it's going to show me all of the projects. It's going to import those two projects. You click Finish, and here they are. So the source code is downloaded. So in the Toronto jar, we don't have anything yet, and in the Toronto robot, though, we have a little bit more than what you see in the one up here, in the temp one. So in our Toronto robot here, what we're trying to do is deal with the joystick problem. So we wanted to write a game controller, and we started writing a game controller, and the game controller class, instead of getting an axis and saying get raw axis 0, what I want to do is pass in a stick and an axis, because on a game controller you have a left stick and a right stick, right? So we made these classes. We made this stick class here that it shows you can either have a single stick if you're a single joystick, or a left stick, or a right stick. And then for the buttons, you can have button 1, button 2, button 3, button 4, ... You can have a lot of buttons. And for Logitech controller, you have Y, X, A, and B are the 4 primary buttons. Right bumper, left bumper, a start button, a back button, and then you can push the joysticks down. So you have a button that's on the left stick and the right stick, right? And we're going to keep expanding the buttons that we've got here. And so now, when I call a game controller, the idea with that is that on the game controller, I can say, give me this stick, give me this axis, and if it's an F310, I'm going to have this sort of mapping. If it's an Xbox One, I'm going to have a different mapping. If it's a Xbox or a
PlayStation,
a PS4, PlayStation, it'll be a different one, right? So the idea there is that we're going to eventually develop this into a pattern and create a factory, and then maybe even pull up the driver station and detect what joystick is connected and automatically instantiate the right class from a factory class.
Wow.
Yeah, so that's kind of where we're going here, but this is just week 1, right?
Yeah.
This is week 1 of 4 weeks. So then the trigger, again, the triggers, I just put an empty class here. It's up to the students to fill it in, and it's going to be probably left trigger, right? Because there's 2 triggers.
Right.
And then in our game controller, we said, okay, I'm going to be able to get a button. I'm going to pass in a button, case X, Y, A, B, and then it's going to return the raw button. But I could also get a trigger as a button. So sometimes you have the trigger, but you don't use it as a trigger. You say if it's greater than 0.3 or something like that, then assume they pressed it and return it as if it's a button, right?
Mm-hmm.
So that way you can, cause something to happen if you're not actually using it in an analog fashion.
Right.
And get POV
Yeah.
returns the get POV. So this is incomplete, and I understand it's incomplete. This is the homework that everyone has for this week, and we're going to see what people come back with as the various joysticks, and hopefully people with different joysticks are going to come back with the different mappings, and we're going to resolve that as part of the next week's work.
That's a cool and useful exercise. Wow.
I think it's cool and useful as well.
Yeah.
So in our chassis subsystem, so let's look at our chassis subsystem. All we did was rename example subsystem to chassis subsystem. So our chassis subsystem here extends subsystem, and it's got two motors. It's got a left motor and a right motor, and we're using old Victor 88 something controllers. And so we have two speed controllers, a left and a right. And in the init, we set our right motor inverted. Do you know why we set it inverted?
Well, because
it's upside down, right?
Yep.
So if we want to drive them forward, we're, rather than having everywhere in the code setting the speed, oh yeah, the right motor's inverted, I have to negate that value. We used to do that kind of thing, and what it does is it just leads to a lot of trouble where not everybody can pick up the code and deal with problems, right? And you end up, why didn't this work? Why is it turning funny? Decide a direction of your robot and decide which end is forward and what the right side is and what the left side is,
mm-hmm.
and then set your inverteds in the initialization method, right? And then that'll help a lot. And then we initted our default command was our default chassis command. So this is going to be our joystick command. So notice how in theirs they said example command. Well, I like to name things properly. So I like the idea of the name default chassis command. And then you see here we could set the speed. So the left motor, we had the set speed that if you pass in one value, it sets the left and right motor. If you pass in two values, it sets them independently. So you can either pass in one and both motors get set to the same thing,
mm-hmm.
and it goes straight forward
mm-hmm.
or backwards, or you pass it in two and it does whatever. So then in our, I know we're almost out of time, but in our class, so we got to look at that class. That's the default chassis command. Here, we require the chassis subsystem, and then in the execute command, we go to the robot OI, get speed and get turn, which in our OI class goes out to get speed, returns the game controller, get stick, left stick, y-axis. So we used one stick. We used the left stick for both the speed and for both the forward, backwards, and for the turning. So that gets both the speed and the turn off of the left stick of the game controller, right? So now we'll go back to our default chassis. So we got our speed and our turn, but what we really need is a left speed and a right speed. So you have to figure out how to map those. And the challenge this week was we put up on the board kind of how we wanted the robot to drive in general. And they're taking that home as homework to try and develop this execute branch that's
mm-hmm.
going to take the joystick values and map them into motor speeds. But just as a little demo, we said if you push the stick either straight, left, or right, then we want to turn the robot. And if we push it straight forward or back, we want to go straight forward or straight back. And there's no sort of, if you push it to 45, it does nothing. It just sits there because we didn't design that yet. Kind of fun. This was just an example, right? So that the students can now take this home, and they're going to build on this and actually design the speed controller, the joystick function that they're looking for, right?
Richard, that's amazing.
Using this framework.
What an incredible amount of resource you've given us today. It's just.
Thank you.
Yeah,
so then, just one last thing. When you're ready to, if you want to catch up to where we are,
yeah.
and you've done this, and you have your Toronto Framework Master, you just go to Team, and then Pull, and it pulls any changes, and it would actually show you the changes.
Oh, just like that.
If there were any, but because we're up to the, yeah, and then you can follow along. If you
Incredible.
have these just sitting there in your Eclipse platform, you can follow along what we're doing every week by just doing a poll and see what we're up to.
Well, just keep commenting that code so we know what's going on.
Yeah, it's not well commented yet, but we're working on that. So hopefully this was a good start and get you going, and
Fantastic.
lots of online resources, and I wish you all the best of luck. And if anyone is listening from the Toronto area and wants to join these robot lessons, you're welcome to join in.
Richard, thank you very much. It's been really, really interesting. You're a fantastic speaker, and these resources are I mean, there's hours and hours of exploration we can go through now, and I really appreciate your time.
Okay.
All
Thank
right.
you very much.
All right, and best of luck to Team 1310. Running
Great.
robotics.
Well, we'll see. We'll see where this year leads. You know, everyone's always hopeful at the beginning of the year. We always enjoy that. We're really looking forward to kickoff.
I know it's not long now. Yeah.
So what do you think they're going to do this year?
Oh, you know, obviously it's something to do with. I think 8-bit computers. I think they're going to bring out the Commodore 64 style graphics and Atari 800s, and it's going to be something based on pixels.
Oh, interesting.
Because, you know,
See,
the first Tech Challenge, they had one of its challenges was to work with glyphs, right? And these little blocks, little pixelated boxes that have to put into a matrix in certain patterns. And I think, oh, that sounds kind of pixely too.
Right. Maybe there'll be 3D pixels that you have to manipulate around the field.
I wonder, yeah.
And I was also thinking you got to put a coin in the slot in auto.
That's a very clever. That's right. Yeah. Hey,
get the game going.
Maybe a coin as big as his gear, eh?
Yeah, but orient it the other way and put it in the right slot to start your game.
Man. You should be writing these things. I wonder if Walt Disney Imagineers are having a hand in this game too.
I don't know. I didn't see them. I didn't see the Disney logo, but I don't know. I would love. Maybe they are. I don't know.
Yeah. Well, it's just a little over a month to go. We're going to find out.
Sure.
Yep.
Okay, Craig. It's been great.
Yeah,
it's been a great night, and hopefully everyone got something out of this.
Thank you so much.
I'm sure
Richard.
you did.
All righty.
Okay.
Okay.
Thank you, Greg. Okay.
Yeah.
Bye.
Well, that was a fantastic introduction to networking, or to Java and all the resources available to you. I'm not a huge Java programmer myself. I wish I could get into it. I did a lot of C++ earlier on in my life, and Unix programming, but Java sounds very cool. So next week, next week we're going to be doing LabVIEW. We got something called a LabVIEW Lounge, so we're going to see if we can provide as many resources in LabVIEW as we just got in Java, and that's going to be a tall bill. So I hope to see you then, and thanks again one more time, Richard. I'm going to let you go.
Okay.
And we're going to sign off till next week. Same time, same place.